That's a big success for everybody. Now we got it back. Now it's up to us to drive it to the comet.
You want to see this clean peak, and that's what we got. You wait a few more seconds and you see this clean carrier signal, and that's all you need to know.
We have no idea what is waiting for us out there. Rosetta will use its navigation camera as it gradually closes in on its target, Comet Churyumov-Gerasimenko, before shifting to the trajectory that will finally bring it to its destination. Then it will start to orbit the comet, map it and characterize it. This will enable us to search for a landing site and land the Philae lander in November 2014. Philae is the part of the Rosetta mission that will land on the comet. So we will really have the opportunity to investigate the primordial dust and ice material on site.
You've got to watch yourself here. This is what we're looking at. 50% of the comet's going to be made of material like this. We can look at the water on the ocean of the Earth and compare that ratio to what we find on comets. Whether it's like sheet ice or it's more dusty ice, possibly this water could have been delivered to the Earth by the comets. This is why we're going to this comet, to see where that water comes from, to see is it connected to Earth at all? And that's then connecting to whether we ourselves are connected to comets maybe, who knows?
With this mission, we're entering new territory. In Berlin, we have built 3 instruments for this lander. The Rollis camera on the bottom of the lander will acquire 6 or 7 images that will reach Earth hours later. The MUPUS device will be hammered into the surface to measure the thermal properties. These will then be refined using the other instruments to understand what kind of environment we've landed on.
The spacecraft is now on a trajectory to the comet, but it doesn't have yet the right velocity to actually arrive at the comet and stay there. We activate our thrusters, the small rockets we have on board, and we accelerate the spacecraft to reach the exact velocity of the comet. And we do an acceleration of about 800 meters per second. It's a lot of acceleration.
We start to see this pinprick in the distance, and then you realize this is reality. It's not a theoretical concept anymore, it's a real comet. We're seeing this pinpoint of light getting closer and closer. It wasn't like this grey potato that we first imagined, that it was actually much more interesting.
It consists of 2 parts. This double structure was not expected, and we all had the same initial thought. How will we land on this? It hasn't made things any easier. We don't want Philae to end up on its back like a beetle or to crash. All these things are much easier to solve on a spherical target than on a very rugged surface with valleys, even canyons, cliffs and crevices. These are difficult conditions.
Therefore, we have a ground reference model here at the Lander Control Center to test all the sequences over and over again. It takes some time, but we have to make sure that it works. The landing sequence will be started at a specific moment. At the same time, the orbiter must adopt a specific orientation, as the lander will be pushed away from the orbiter.